So, welcome everyone. I will be presenting our work on decomposing numerical abstract domains. It's a joint work with my supervisors Markus Püschel and Martin Vechev, both from the Department of Computer Science in ETH Zurich. Does not work. Numerical abstract domains are crucial part of modern static analyzers. As a result, there is considerable interest in designing them. So a number of numerical abstract domains exist in that offer different kind of expressivity. So for example, we have interval domain which only encodes upper and lower bounds between program variables. There is also polyhedra domain that can capture any kind of linear relationship between program variables. In between these two, there are so-called weakly expressive domains like Octagon that only can have constraints between two variables, and the coefficient should be plus and minus 1. The list shown here is not exhaustive. There are many more domains that already exist and maybe will be discovered in future. One crucial aspect of static analysis with numerical domains is the expressivity of the domain. But apart from this, another crucial component that determines the cost of numerical domain analysis is the cost of domain transformers. So let's take an example of octagon domain that only encodes constraints between two variables, and I have an if statement between three variables, right? So the usual way to implement transformer for a conditional statement is just add the constraint to the input abstract element. In this case, the constraint cannot be captured by the octagon domain. So what happens is that we try to approximate the addition of this constraint to the input element. So now there are different ways to handle this approximation. There is always best way, which has worst case exponential cost. So in this case, the best transformer for this conditional statement will add three constraints. Since it defies why the octagon domain was created for efficiency, the standard way to approximate it, which does so in quadratic time, will trade off some precision for efficiency and add only one constraint instead of three. Of course, if you are hopeless and really don't want to handle this statement, you can set the output to top and later can say that the static analysis doesn't work. So the point here is that there is no one way to implement domain transformers, and there is always a choice between cost and precision. So even if the domain is very less expressive, like the octagon domain, you can still get expensive transformers. So recently, the performance of numerical domains have been increased by the concept of online decomposition. It is based on a simple observation that usually the analysis is very sparse, so not all program variables get related to each other during analysis. And what you can do is you can decompose the set of program variables into disjoint subsets, which we call blocks, such that the large abstract element decomposes into smaller pieces, which we call factors. So in this case, it's the same abstract input element from the previous slide, and one can see that there is no constraint between x1 and x3 and x4. So you can decompose the abstract element into two pieces. And now we apply the standard transformer. The standard transformer only adds constraints between x3 and x4. So we don't need to work on the on the full abstract element, but only on a part of it. In this case, the part that corresponds to applying the transformer is only the second factor. I mean, this is a small example, but you can imagine if the abstract element is very large, there is a great reduction in complexity. So this concept of online decomposition has been applied in previous work in POPL'18 for the octagon analysis, and for polyhedra analysis in SAS 2003 and POPL last year. The limitation of both these approaches is that they are tailored for the particular implementation, right? So having online decomposition for numerical domain is very time consuming and tedious. So whatever effort is spent in designing this online decomposition cannot be reused for any new domain, right? So just to give you motivation why this does not work, In this case, the POPL'18 online decomposition knows that it has access to the definition of the transformer, and it knows that it will not add any constraint for variable x2, right? So then it does not work on the first factor. But if I make another transformer that actually adds a constraint for x2, then this kind of decomposition will not work. Okay. So this stems from the fact that usually when you design numerical abstract domains and their transformers, you have always cost and precision trade-off. So depending on your application, you design them tailored so that they meet your requirements, right? This is kind of ad hoc. So of course, the prior work cannot be generalized for any new domain and a new implementation of that domain. So what is required is a universal construction for decomposing any numerical abstract domain. So this is what we achieve in this work. So we produce, we introduce a black box construction that produces decomposed analysis based on the original non-decomposed analysis. Of course, we assume that the original analysis is sound. Otherwise, we will also be unsound. So it is black box in the sense that it does not require any access to how the transformer is implemented. So if your transformer is implemented with graphs or with matrices, it doesn't matter, right? And we provide some guarantees that it is always sound, and it has the same precision as the original analysis in most practical conditions. We provide specifications when you can identify when your transformer will not lose any precision with our construction. Hopefully this can help you in designing such transformers that have the same precision. So we have used this construction to implement decomposed analysis for polyhedra, octagon, and Jones domain. It is available as part of library Alina and can be downloaded from the given URL. So just to give a flavor of the results that you can get with decomposed analysis, let's look at this representative benchmark, which has more than 30,000 lines of code and more than 550 variables. If you do original non-decomposed analysis with polyhedra, it takes more than 6,000 seconds. But with the decomposed analysis, you can do the same thing and get the same invariance in 4 seconds. Similarly, for the octagon domain, the time reduces from 28 seconds to 2 seconds. And for Jones, also we get some speed up. It's easy to note that the more expressive and expensive the domain, the more is the speed up, right? So before proceeding further, I would like to give some background. So the abstract elements or the abstract domains that we consider in domain in this paper contains conjunction of finite number of linear constraints. I think these junctions can also be handled, but we do not handle them currently. And the concretization function for the domain should be mean preserving, which is a very standard assumption. And similarly, the abstract elements in the domain should be ordered semantically. So if they are ordered in the abstract, they should also be added in the concrete. Otherwise, this is also a standard assumption. Otherwise, it is hard to guarantee that actually the analysis will converge. So more background on online decomposition. So let's look at again the octagon domain, and we have an element. So what we can do is we have a set of constraints in the abstract element, and we can just put two variables that occur in the same constraint together and compute a finesse partition, right? But usually this is very expensive to compute. So what online decomposition does is it maintains a permissible partition. Permissible partition is coarser than finesse partition. So if two variables have a constraint between them, they will occur in the same block. But if two variables occur in the same block, they may not have a constraint between them. So in this case, you have x3 and x4 in the same block, but they do not have any constraint between them. An invalid partition in this case will have x1 and x2 in different blocks, right? Here x1 and x2 are having a constraint between them, but they are in different blocks. So this is kind of invalid partition. So because maintaining the finesse partition is expensive and mainly negates the effect of having decomposition, online decomposition usually maintains permissible partitions. Okay, so what does it mean by decomposable transformers? So we say that a transformer is decomposable with respect to an input I if it produces an output that does not have a trivial partition. Trivial partition means that it's only one block with all variables together. So let's look at this polyhedra domain example with 5 variables. We have a decomposed input and a if statement. So for the same input, it is perfectly possible to have 2 sound transformers. One gives you non-decomposable output, and the other gives you decomposable output, right? So there are 2 ways to obtain decomposable transformers. The first way is, of course, to design them from scratch, right? That's very time consuming. So the approach that we take in this work is we construct them from non-decomposed transformers, and the typical implementation of a domain has around 30-40 transformers. Most of them are straightforward to handle. In the paper, we show how we handle. Of course, our implementation handles online decomposition for all transformers. In the paper, we show how we handle for 5 interesting transformers, which are conditional assignment, meet, join, and widening. In this presentation, I will be presenting how our construction works for conditional mainly. So suppose we have an abstract element I in any domain D, and it has a permissible partition pi bar, and we have a linear conditional statement. Then from this, I extract block bcont, which basically contains all the variables that occur in this conditional statement. So in this case, the if statement is x3 plus x6 is less than or equal to 0. So your bcont is just x3 and x6 because they occur in the conditional statement. And out of this bcont, I do transitive closure of bcont with respect to the permissible partition pi bar to obtain another block b star cont. So b star cont will merge all the blocks in the input partition that have a empty intersection with bcont. So in this case, the first block x1, x2, x3, and the last block x6 has a non-empty intersection. So b star cont is x1, x2, x3, and x6, right? So our decomposed conditional transformer, what it does is it applies the original transformer on the part of the input that corresponds to the block b star cont, and it keeps the rest as they are, right? It's easy to see. What we do is we just apply the original transformer on a smaller element, so it's agnostic to the data structure or algorithm that is used, right? We don't really care about it. In the end, and the output partition contains b star cont as a block, and all other blocks that have an empty intersection with the b star cont. So to just give an example, let's suppose we have an element in the octagon domain which is partitioned into 2 blocks in 2 factors, and we have a if statement x3 is less than or equal to 0. In this case, b star cont is x2, x3, right? So we will apply the standard octagon transformer on only the second part, our decomposed transformer. It adds constraint x3 is less than or equal to 0. Now the standard octagon transformer also does closure of the constraints. In this case, you don't get any new constraints, so this will be the output of our decomposed transformer. So since we do not apply the original transformer on the full element, it's easy to see that we will not produce the same abstract element in terms of set of constraints, but we can still produce an abstract element which is equivalent to what you get by applying on the full element in the concrete. For this, we require that the original transformer should satisfy certain properties, and these properties usually hold in practice. So first property says is when you apply the original transformer on the input element, it keeps all the constraints, and then it adds non-redundant constraints only corresponding to b star cont, right? And it can add any more redundant constraint between variables that are not in b star cont. We really don't care because it does not change the concretization of the abstract element. The second condition says that you should be able to obtain the set of non-redundant constraints added by the transformer by just applying it on b star cont. the factor corresponding to B star cont, right? So I can give an example of the same example. So we have the same input element, and now we will apply the original transformer on the full element, right? So when you apply on the full element, it adds x3 less than or equal to 0, and then it does closure. So closure introduces this constraint x1 plus x3 is less than or equal to 0. So this output element has trivial partition, right? Because all variables have a constraint with each other. But what we can observe is that the constraint x1 plus x3 that is added by the closure is redundant, because I already have constraint x1 is less than or equal to 0 and x3 less than or equal to 0. So even if you remove this constraint, the concretization really doesn't change. So one can convince that this satisfies our second condition also. So for this standard octagon transformer, if you do our decomposition, you get the same abstract, equivalent abstract element that has the same concretization. So we have similar theorems and construction for the other transformer. I will not describe them here. Besides this, what we do is we have some refinement where we, after computing the output, we refine the output partition for assignment and joint. This allows us to be faster than previous work on polyhedra and octagon. These are described in the paper, but I will not really discuss them here. So for experimental evaluation, we use the Crab LLVM analyzer, which is part of the larger C-Horn verification framework. It does inter-procedural analysis of C program by converting them to LLVM bit code. The benchmarks that we used for evaluating were taken from the popular software verification competition, and we chose two categories which are interesting for numerical analysis: Linux device drivers and control flow. For comparing against polyhedra analysis, we used the non-decomposed transformers from Parma polyhedra library and decomposed one from our previous work from last year. For the octagon domain, we took non-decomposed and decomposed transformers both from POPL'18, and for Jones, we implemented everything ourselves. So in terms of results, and we used for the experiments memory limit of 12 gigabyte and timeout of 4 hours. So in terms of results, we have I show here 12 benchmarks. So non-decomposed analysis with PPL either runs out of memory or is times out on 8 out of 12 benchmarks. So when PPL runs out of memory, we report that the speedup is infinite because the given analysis can never finish on the given machine. We provide lower bound for when the analysis times out. Of course, we get large speedups compared to PPL, but also interesting to see that with our refinements, we get also considerably significant speedup over our previous year's work. And similarly for octagon domain, we get significant speedup. The largest speedup is 40 times with respect to non-decomposed analysis. There is significant speedup with compared to decomposed transformers also, and the maximum is 2 times. For the Jones domain, again we get speedups, but again not so much as octagon. The maximum is 6 times. So in terms of contribution in this work, we introduced a black box construction for producing decomposed analysis from non-decomposed analysis. That is always sound, and under practical conditions, it has the same precision as original analysis, right? We have implementation of polyhedra, octagon, and Jones domain available online as part of Alina library, and there is significant speedup. I would also like to say that for the polyhedra domain, we have actually more optimization that are not described in the paper. So the version that is available in the repository can be up to 4 times faster than what we have at the moment. So with it, I would conclude this talk. Thanks for your attention.
I have a question, a nice one. Do you consider also the reduction with nonlinear domains, for example, the simple congruences? Because if you take intervals you decompose into, then the reduction is lost.
Yeah. So this is something we started with, and I think with if we invest more time, this something can be looked into, and I have a good feeling about it, but we don't consider it at the moment.
Oh, next POPL paper. Huh?
Thank you.
Any other questions? All right, then we'll do a question from Slido.
Okay.
So the question is, can you use your technique to decompose the reduced product of two domains?
Sure. I mean, the original plan for this work was to also consider reduced product of a subpolyhedra domain with pointer analysis or array analysis, but that cannot fit into this paper, but certainly it can be done.
All right.
Okay.
Since we are a little bit short on time due to the technical delay, so
Okay.
let's thank you.
Okay.